Good morning, Amherst. Welcome to electroplating, electrolysis, electrolytic operations. This is going to be a little bit of a different lesson today. So what I want you to do is I want you to follow through with your packets, and this is kind of a note day. So turn to the electroplating part of the electrochemistry packet, and we're going to go through electroplating, electrolysis of fused or melted salt, electrolysis of water, and electrolysis of brine in a second salt solution, another brine solution. All right, and then your post a key to the vocabulary stuff here. Your homework is going to be the Regents Review. So this is going to be a little bit different type lesson than usual. All right, so let's talk about electroplating. First of all, any electrolytic process. This is a dead giveaway. You see this? Dead giveaway that this is an electrolytic, not a voltaic process. If you see a power source, it requires a power source. It's not going to happen by itself. The power source, the purpose of the power source is to make the electrons move around. Now, you are all about the age where you start to drive, and I guess maybe jumping a car battery is a skill that you may or may not have acquired, and I guess with the power packs things are a little bit different, but some things will hold true. If you have a dead battery and you need to jump, you hook up the red cable to the red cable, you hook up the black cable to the black cable, red to red, black to black, positive to positive, negative to negative. So your power source, your battery, will have a positive side and a negative side. So you're going to hook up positive to positive and negative to negative. I hope that comes through. I don't know if you can see that on there or not, but okay, positive to positive, negative to negative, you go. This is actually part of the battery. This should kind of be connected. What is negative? Well, electrons are negative. The electrons are always coming this way. Electrons are negative. This is the negative electrode. The cat, Leo, we're going to coat him, in this example, we're coating him with copper. He's not very happy. Why do I make this the cat? Because the cat is the cathode. So Leo is getting a bright, shiny red coat, red copper. And the electrons, this is a circuit. This is direct current, so the electrons are coming back this way. Electrons are going back that way. Positive to positive, negative to negative. Electrons are negative. The electrons go from the negative terminal of the power source and they return to the positive. That's always going to hold true. So the cathode, of course, is where reduction occurs. And if that's the cathode, then this must be the anode. And this is where oxidation is going to occur. Red cat and ox, always, always, always. On the diagram, draw an arrow that shows the direction of the flow of electrons. Got it. Label it E. Got it. Yeah, that's done. Draw an arrow that shows the direction of cation flow and label it Cu. Well, in solution, it's not set up very well, but we want to coat, we want to plate the cathode with copper. So we're going to take our cathode, our cat here, and we're going to give him a brand spanking new shiny coat. Well, our anode here has to be a piece of copper. And in solution, I've got to have copper ions. We're going to make these copper plus 2 ions. And those copper plus 2 ions are going to be attracted to the electrons, and they are going to grab those electrons on the surface of the cat, and they are going to start forming a brand spanking shiny new coat on Leo. Leo's going to get heavier. Draw an arrow that shows the direction of the cation flow. Done. Write the equation for the anode half reaction. The anode oxidation is going to occur, so you're going to have copper 0 becoming copper plus 2 and 2 electrons. No, that is definitely not the anode reaction. Stop. Reverse that. Anode is oxidation. Why am I writing reduction? Oh, no, that was oxidation. Copper is still backwards. Sorry. Copper 0, yes, is becoming... Stop second guessing yourself, Burger. Copper plus 2 and 2 electrons. Let's talk about voltage. Let's pull out the supplemental reference table and find copper plus 2. Copper plus 2, there you are. Now that's the reduction, and that's positive 0.3, so I reverse that. That's going to be negative 0.3 volts. And for the cathode, the reduction, it's the exact opposite. So you're going to have copper plus 2 and 2 electrons becoming copper 0, and that's going to be positive 0.4 volts. So if you think about the net ionic equation for this, well, let's think about this for a second. I'll get a smaller pencil so I can write this a little bit better. Here's my oxidation. Copper 0 goes to copper plus 2 electrons negative 0.34 volts. Here's my reduction. Copper plus 2 electrons goes to copper 0. That's positive 0.34 volts. If I add those together, well, the coppers are going to cancel. The copper plus 2s are going to cancel. The electrons are going to cancel. And the volts are going to cancel. There is nothing for a net ionic equation. It's just not there. So the net voltage for the electroplating process is 0, but those electrons aren't going to move themselves. The power source is simply to create the circuit, to give the driving force to make the electrons want to go onto the surface of the cathode. So if the cathode is getting coated with brand new, spanking new copper ions, it's going to get heavier. If the anode is here and it's oxidizing away to replace those copper ions in solution, it's going to get lighter. So what's happening to the anode? It's going to decrease because it's oxidizing. It becomes Cu plus 2 ions in solution. Not enough room to write there, huh? The mass of the cathode is going to increase. Why? Because Cu plus 2 ions become Cu0 atoms on the surface of the cathode. What happens to the concentration of the ions? They remain the same, okay? They get replaced. So Cu plus 2 ions lost equal Cu plus 2 ions gained. Every time an ion from solution goes onto the cathode, the anode replaces it. So much for electroplating. It's kind of cool to do it in school, but we don't have that option this year. Moving on. Let's talk about the electrolysis of fused, like fusion as in solid to liquid, melted salt. So first thing you want to note is that fused melted salt, this is a pure substance still, it's liquid. So when you have liquid salt, what's available to you? You have sodium ions and chloride ions. Those are the only players in the game. So you can see recurring theme here. Here's my power source. Negative goes with negative. Positive goes with positive. What is negative? Electrons are negative. There they are. That's why this is the negative electrode. And they're coming back this way. You'll see this recurring theme. Okay, so I've got a direct current circuit going on here. And in solution, I've got some sodium ions. And I've got some chloride ions. And they're going to be all over the place. I just happened to put them together. Now, probably should have drawn those the other way. So I'll put some more sodium here. Some more sodium here. Some more chloride here. Some more chloride here. They're not going to be heterogeneously distributed like that. They're going to be homogenized, but it doesn't really matter. What's going to happen? Who is interested in the negative ions? The sodium, the negative electrons. The sodium ions are positive. They're going to want to gain those electrons, and they're going to start forming on the surface. Oh, okay, so they're gaining electrons there. This must be the cathode. And what's going to happen? Who's attracted to the positive? Well, the chloride ions are attracted to the positive. They're going to give away their electrons. They're going to form chlorine gas, and don't breathe that. It's mustard gas. That'll kill you. Chlorine gas is going to bubble off there, and the electrons are going to go back to the power source. So this is a loss of electrons here. This must be the anode. Okay, once again, red cat, that's where reduction is occurring. And ox, that's where oxidation is occurring. In the electrolytic cell, what kind of reaction occurs at the anode? Well, it's always oxidation. At the cathode, it's always reduction. Some things hold true. What is the charge of the anode? The anode is positive. What is the charge of the cathode? The cathode is negative. Write the equation for the electrolysis of fused molten salt. Okay, well, I'm going to need my supplemental table 6. I was calling it table J the other day, but this was a much better table. Okay, so what do you want to start with? We'll start with reduction. Who's getting reduced? Sodium ions are getting reduced. So you go find it. You've got sodium positive, gains an electron, becomes sodium 0. And according to the supplemental table, that reduction right there is negative 2.71 volts. So my oxidation is the chloride, and that's going to be up toward the top. There's chloride, so I have to reverse it. So it's going to be 2 chloride negative are going to go to Cl2, 0, and 2 electrons, and that's going to be negative, what's it say, 1.36 volts. Now I've got 2 electrons there, I've got 1 here, so I'm going to have to double this one. Don't double your voltage, don't double your voltage, don't double your voltage. So it's going to be 2 Na positive plus 2 electrons goes to 2 Na0, and that's still going to be negative 2.71 volts. And this is 2 Cl minuses going to Cl2, 0, and 2 electrons, and that's going to be negative 1.36 volts. And you add those together, and the electrons are going to cancel, so my net ionic equation is going to be 2 Na positives plus 2 Cl minuses go to 2, weird thing going on the paper there, 2 Na zeros and 2 Cl, I'm sorry, not 2 Cl, this is going to be Cl2, 0, and 2.71 and 1.36, that is going to be a whopping negative 4.07 volts. And it's negative, so it requires energy, so that is going to be endothermic. It's not going to happen by itself. That's why you have a power source. Write the equation for the anode half reaction. Well, we just did that. Anode is oxidation, so I had 2 Cl minus goes to Cl2, 0, plus 2 electrons at negative 1.36 volts. Name the product formed. Well, that is chlorine gas, or chlorine molecules, neutral. Write the equation for the cathode. Cathode is going to be reduction. You want to write the double one? Sure, okay. 2 Na positive plus 2 electrons goes to 2 Na0, and that is going to be negative 2.71 volts. What is the product formed? Sodium atoms. So, little sidebar here. Why do they do this? Group 1 and group 17 atoms, or molecules, or elements is a better way to say that. They're very reactive. You never find them in nature. This shows up in the ACS from time to time. How do you get samples of sodium? I think in lab we had done some demonstrations with exploding sodium and lithium and potassium. You'll never find a piece of sodium in the ground. So how do you do that? You either take some salt water, which we'll do next, or you take some pure salt and you melt it and you run some electricity into it and you separate it back into its component elements. You'll never find chlorine in nature, you'll never find sodium in nature, but if you take a salt of chlorine, you melt it, put some electricity into it, you'll get both of those elements back. They're not going to want to stay that way. They're highly reactive, but that's okay. Which substance in the reaction is oxidized? Who got oxidized? Chloride ions got oxidized. Who got reduced? Sodium Na positive ions. Okay? Electrolysis of fused salt. When they say fused, it's pure salt. But you know what? You have to get up over 800 degrees Celsius to melt salt. Ionic bonds are strong. This is probably not the easiest way to get some chlorine gas. So let's go to the next one. Well, here's pure water. This is a little bit different. You could do pure water a lot of different ways. You're going to see a bunch of different diagrams. This is called a Hoffman apparatus, I believe. It's just basically separating the water so you can get the hydrogen and the oxygen into different containers. You'll notice the hydrogen is produced in twice the volume of the oxygen, but literally you could just take a beaker and put some water into it, hook it up to a power source, and put some electrodes into it, and you would get one side bubbling off hydrogen gas and the other side bubbling off oxygen gas. And you'll see sometimes, you'll see, like if you have a bigger beaker, you can have a test tube here and fill it up with water so there's no airspace in there. And if you have a power source here and you run your electrodes like this and you run your electrodes like this, you can make some hydrogen there and have as much oxygen there. It's a 2-to-1 stoic because when you break down water, you're going to get twice as much hydrogen as oxygen. If you think about this, 2H2O, if I decompose it, I'm going to get 2H2 and O2. So twice as many moles of hydrogen is going to occupy twice the volume. That's why this volume is twice as big as this. They're under the same conditions of temperature and pressure. So let's talk about a power supply. They're telling me that this is the cathode, and the cathode is where electrons are gained. The cathode is always negative, which means the electrons were going this way, and this must have been the negative terminal. The anode is positive, which means electrons were returning this way. So this must be positive. This is not a fantastic diagram, but that's okay. So what do we have in solution? We have water molecules. So let's see what's going on here now. Go to your supplemental table. I want you to make a mark, two different marks. Right up here, first of all, 4H positive plus O2, 4 electrons, 2H2O. This is the one that's going to be the oxidation. We're going to reverse this one. We're going to break this water apart, lose some electrons, form oxygen gas, and leave some hydrogen ions in solution. Now go down toward the bottom, and let's mark this one, 2H2O. We're going to gain some electrons here, produce some hydroxide ions, and some hydrogen gas, okay? Put marks next to those two. Now let's think about this for a second. I'm going to reverse that one, and I'm going to be producing hydrogen ions. And in this one, I'm going to be producing hydroxide ions. We know that water, H2O, can also be written HOH. So if part of the process is producing hydrogen and part of the process is producing hydrogen, you're going to break apart some waters, but some other waters are going to reform. So label the electron flow and the ion flow. I've got the electron flow. Let's talk about the ion flow. Let's do the half reactions first. The anode, that's where oxidation is going to occur. That's my top one. So I'm going to take that top equation, I'm going to flip it. So it's going to be an oxidation where you have 2H2O is going to form 4H positive plus O2 plus 4 electrons. Flip the sign of the voltage, that's going to be negative 1.23 volts. Write the equation for the cathode. Well, that's going to be reduction. Go down to the bottom, and you're going to see that's 2H2O plus 2 electrons goes to 2OH minus plus H2, and that's going to be negative 0.83 volts. Now I've got 4 electrons up here, I've got 2 electrons here, so I'm going to double this one. Do not double the voltage, never double the voltage, never double the voltage. So this is going to be 4H2O plus 4 electrons goes to 4OH minus and 2H2, and still negative 0.83 volts. Now I've got 4 electrons here, and I've got 4 electrons there, so they're going to cancel out. But think about my net ionic equation here. So I'm going to rewrite both of these. All right, so here's my oxidation. I've got 2H2O goes to 4H positive plus O2 plus 4 electrons, and that's negative 1.23 volts. Here's my reduction. I've got 4H2O plus 4 electrons goes to 4OH minus plus 2H2 at negative 0.83 volts. So over here, my electrons are going to cancel, but these are going to reform 4 water molecules. So I'm going to have, if I add them together, I have 6H2O goes to 4H2O plus O2 plus 2H2 at a whopping negative 2.06 volts. And if I subtract off 4 waters from both sides, just to kind of reduce that equation, my real net ionic equation is going to be 2H2O goes to O2 plus 2H2. Hands are ahead of my head today, 2H2. And that's still going to be a whopping negative 2.06 volts. Hey, that's the equation we had up here. So it only takes about 2 volts to break apart pure water. But it takes volts, so this reaction is endothermic. Now let's talk about that ion flow. So at the oxidation at the anode, it looks like we had some hydrogen ions coming off of there. So here you're going to say, oh, okay, H positive are coming this way. And at the cathode reduction, we had some hydroxide ions coming off of there. So the OH ions are coming off of there, and they're going to reform water. You'll see different diagrams in the reagents, sometimes in just a beaker, sometimes in different test tubes. It's really not that important, and quite frankly, the voltage goes well beyond what we're going to do in any reagents exam, but it's not that hard to figure out. Just remember, don't use the hydrogen zero reference half cell for the electrolysis of water. That's not what's happening. You got these two. Mark those in your supplemental table. Next, electrolysis of brine. Brine is just salt water. So like 3/4 of the earth is covered with salt water. Pretty easy to come by. Turns out it's a good industrial process because you produce some very useful things. But let's think about what's here. This is a mixture. This is not a pure substance anymore. So what's available to you are Na positive, Cl minus, and H2O. And you're going to put some electricity into there. So, okay, here's negative. This is going to be negative. Here's positive. This is going to be positive. What's negative? Electrons are negative. Send them this way. Bring them back this way. That's always true. So you have to ask yourself, okay, positive. Well, in solution here, I've got Na positive, I've got Cl minus, and I've got H2O. Who's attracted to the electrons? And you might think the Na positive is going to be attracted to the electrons, and that's a good thought, except look here. Sodium positive, to gain electrons, it requires 2.71 volts. Remember, sodium is group 1, so my potential reduction here, Na positive plus electron, becomes Na0, but that's going to cost me negative 2.71 volts. If I look at the equation that I just used in the last one, here's sodium, move up just a little bit, here's water. I can take 2 waters and I can gain 2 electrons and I can form 2 OH minuses and hydrogen gas, and that's only going to cost me negative 0.83 volts. Well, it turns out this is a lot easier to do. So when you've got choices, of course, path of least resistance, what's going to happen is you're going to break apart the water before you're going to try to reduce the sodium ions. So your products here, you're going to oxidize the chlorine. The chlorides are going to become chlorine, but you're going to break apart the water. So what's going to happen here? All right, well, this is the easier reduction. So write the equation for the electrolysis. So, well, I prefer to do the half reactions first. Let's start down at the bottom. Cathode, this is where reduction is going to occur. It's easier to reduce the water. So I'm going to have 2 H2O plus 2 electrons. I'm going to go to 2 OH minus plus H2 at negative 0.83 volts. So at the cathode, okay, where electrons are going to be gained, this is going to be my cathode, right? Red cat. If that's the cathode, this must be the anode. Anox. At my cathode, I'm going to be producing hydrogen gas. So the water molecules are going to be moving this way. And coming up out of here, you're going to get some hydrogen gas. And, you know, hydrogen burns, so that's a good thing. I guess it's a fuel. Talked to the Hindenburg about that. It was kind of a dangerous fuel. But also coming off of there, you're going to have some OH minus ions. Okay, what about the anode? This is where my oxidation is going to occur. Who's going to get oxidized? It's going to be the chloride ions. So find your chloride here and reverse it. 2 Cl minuses are going to form Cl2 and 2 electrons, and chloride is going to cost me, if I flip that, it's going to be negative 1.36 volts. So 2 electrons, I guess my net ionic equation, I think we should probably reverse these questions here. It's going to be 2 Cl minus plus 2 H2O goes to Cl2 gas. Ooh, okay. That's chlorine gas, mustard gas, it'll kill you. The electrons cancel. Plus 2 OH minus plus hydrogen gas, and once again, that was going to cost me chlorides, cost negative 1. Oh no, add these together. Sorry. Little mind going on there. So what's 1.36 and 0.8, negative 2.19 volts total. So oxidation at my anode, I've got some chlorine gas bubbling off of there. Don't breathe that, it'll kill you. All right. What happened to the sodium? It's just a spectator ion. So when you think about this, the products for doing electrolysis of brine, in solution you've got NaOH. That's a very useful base. And you're producing hydrogen gas and chlorine gas. So the products for the electrolysis of brine are hydrogen, chlorine, and sodium hydroxide. Those are very useful for industrial processes. That's why it's been studied so much. It's not part of the Regents curriculum, but not beyond our capability. Last one for today, electrolysis of a salt solution Ki. Once again, this is just another brine, so what's available to you? K positive, I minus, and H2O. And you're going to find out potassium, that's going to cost you negative 2.93 volts to reduce that. And once again, water was only negative 0.83 volts. So this is going to be the species that undergoes reduction. So your products here are going to be, once again, hydrogen gas, right? Instead of chlorine gas, you're going to give iodine solid, and then you're going to be left with KOH in solution. Another useful base. So negative goes with negative, positive goes with positive. Electrons are negative, they go this way, they come back this way. So electrons are down here, that's negative. This is my cathode. That's where reduction is going to occur. This is my anode. That's where my oxidation is going to occur. They want the overall, they want the anode, they want the cathode. Once again, these are written kind of backwards. I might do them the other way, but the easier reduction was water. That's my water equation again, 2H2O plus 2 electrons go to 2OH minus and H2, and that was going to cost me 0.83 volts. My anode, my oxidation, my iodide ions are going to get oxidized. Find those on your supplemental table. Iodides, right here, you're going to have to flip it. So 2I minus, I'm going to go to I2 plus 2 electrons. And what was that? Iodine. Oh, it's going to cost me, because I flipped it, 0.54 volts, negative 0.54 volts. 2 electrons. Let's do my net ionic equation. So this was my reduction. This was my oxidation. My net ionic equation over here. So I've got 2I minus plus 2H2O goes to I20 elemental iodine plus 2OH minus plus H2 elemental hydrogen. Let's add those together, 0.83 and 0.54. Oh, math. 1.37. So it's going to be negative 1.37 volts. This one's going to cost me. So in solution, I had some K positive, I had some I minuses, and I had some H2O. The H2O are the ones that are going to get reduced. They're going to come this way. Who's coming off of there? Well, you've got hydrogen gas coming off of there. And then you've also got some OH minus coming off of there. And then over here, your iodides are going to go this way. And you're going to have some I2s coming off of there. That's going to be a solid. It'll probably sink. But left in solution, you've got KOH. All right, that's electrolysis of a second brine. Just remember, when you've got a salt in water, the water is a player in the game. It's easier to break apart the water than it is to try and get those alkali metals into their elemental form. All right, a little bit of vocabulary. Maybe I won't screw it up this time. Let's see. Flow of electric charge. Well, that's a current. Electric current. Okay. In one direction, that's called direct current. When it goes back and forth, that's alternating current, and we can thank Nikola Tesla for that, although they screwed him out of everything, and Thomas Edison was not a nice guy. But that's a whole other story. If the flow proceeds in one direction, that's direct current. Yeah, Tesla, you'll see a statue of him at Niagara Falls. And he died broke and penniless, and horrible story there. Look that up on the History Channel. The carrying of electrons through the substance, such as copper and silver, those are metals, so that's metallic conduction. Carrying of positively and negatively charged particles of an electrolyte, I would say. It's called ionic conduction. See, the vocab, it's not that important. Understand the concept, get the vocabulary last. The process by which flowing charges bring about a redox reaction, that's called electrolysis. It's when you make a non-spontaneous redox reaction occur by the application of external power sources. In such a process, the battery wire and metal strips, the stuff on the outside, that's the external circuit. The electrolyte inside, that's the internal circuit. And I have to ask myself, who really cares? Inside, outside, it's all part of the circuit. The use of this process to coat or to plate material with a layer of metals is called electroplating. The negative electrode, that's always negative because it's where the electrons are. That's where reduction occurs. That's going to be the cathode. The negative electrode at which reduction occurs is called the cathode. An ion attracted to this is called, well, a positive ion is going to be attracted to it. Positive ions are cathode, or cations. Cations go toward the cathode. The positive electrode at which oxidation occurs is called the anode. An ion attracted to it is called an anion. Negative ions are attracted to the positive anode. An oxidation or reduction that is part of a complete oxidation reaction. An oxidation or reduction, those are half of it, so they're called a half reaction. Is that a choice? Yeah, half reaction. Okay, so that's the vocab. Your homework, due tomorrow. Regents Review. The stuff we've just done is remarkably more difficult than Regents Review. You will find that these questions are very superficial. Okay, so you've got 1, 2, 3, 4. It looks a lot, 5 pages, but there aren't that many questions there. It's 7, 8, 9, 10 questions, something like that. Okay, due tomorrow. I'll post a key later, and I guess I'll post a key to what we just did, another version of it, but you should have been filling it out along the way. Take care. Talk soon.